I'm Rebecca, and I'm going to talk to you about illustrating computer system architecture with DLSym. DLSym is a digital logic simulator which is used in computer organizations courses at Oberlin College. That means that it needs to cover material from the most basic, or computer organizations courses, cover material from the most basic logic circuits up to things like CPU design to system-level design involving how devices communicate with each other along buses. There are a number of good tools that are used to demonstrate to classrooms and other settings each of these areas, but DLSym is designed to cover all of them. So here's an example of the lowest level of DLSym, where you can build circuits using gates and flip-flops. This is simulating a 4-bit register, so it can hold 4 bits of saved data. Moving on, through the use of plugins, which are written in Java and can be added to DLSym, more complicated circuits can be built without having to build each component out of gates. For example, this is an older project which simulates a MIT CPU. You can see all of these little boxes around here are made as plugins. Note, like, this is a register or an ALU. These things can be built out of the simple gate parts just being connected together, but since the focus of a project like this is on how all of these parts communicate with each other to make up the CPU, they're abstracted away through the use of plugins. So my project is on showing how DLSym can be used to demonstrate the system architecture level, which consists of communication between devices like the CPU, memory, and I/O devices along a bus. Because the focus of this project is on how these devices communicate with each other, we created them as plugins, again, to abstract away the detail about how things like the CPU and the memory work, so you can see really how they communicate with each other. So the first circuit I'm going to show you is simulating a CPU communicating with memory. If we hit the reset button, you can see it's initialized from a file, and this CPU is performing a simple sort algorithm on the memory. So you can see now the data is being sorted using insertion sort. The CPU is communicating with the memory by putting various values on its output pins, such as the address, and it can set either read or write to 1. In the case of a write, it puts a data value, and then so it can read in something from the memory, decide what to do with it, write it back out in a new order. Moving on, you may be wondering how you make a plugin. Plugins are written in Java, and a few of the most important things you have to specify in a plugin is how many inputs and outputs you want the plugin to have, and there's a method called eval bundle, which specifies how your outputs need to change in response to your inputs. By developing a protocol, you can allow for successful communication between the plugins. Like I mentioned earlier with the CPU and the memory, it has to put out the address and then put read to 1. Then the memory plugin knows that the CPU is trying to do a read, so it can get the data value, put it on its pin, put a signal out saying that it's ready, then the CPU can get that data. Other devices which communicate using the bus include I/O devices. The CPU communicates to an I/O device by writing to a number of different registers that it has, and then the CPU the I/O device, when it receives input being put in, it sends what's called an interrupt to the CPU. When the CPU gets the interrupt, it sends an acknowledgement back to the device, and then it can handle that interrupt in whatever way it chooses. So this circuit is showing an example. This CPU is running a sort in this memory. When somebody types something into the input console, then the CPU receives that interrupt, and it handles it by reading in the input and then copying it to the output console. In order to have multiple interrupts all sending requests to the same CPU, you can either have a bunch of different request lines on the CPU, or you can have what's called an interrupt controller, which takes in a bunch of them and sends out only one of them to the CPU. The interrupt controller determines which interrupt should be processed first by a priority that it knows. So here's a okay. Created an example circuit of that shows the okay, here you go. This is showing a test algorithm for the interrupt controller. So you can see there's two different I/O consoles as before. This CPU is sorting data in this memory. When it receives an interrupt, it's passed through the interrupt controller and goes to the CPU, and it handles the interrupt by this time copying it to the output of the other window. So it's able to handle if something is typed into both of the windows, it will copy both of them into the correct spot. The next circuit I wanted to demonstrate is the bus arbiter plugin. Up till now, we've been assuming that only one device wants to become the bus master, which means it's the device which is putting data onto the bus. In reality, you may have multiple devices that want to put data onto the bus, like request values from memory or something, and if all of them just went on doing it, you'd see how they'd get all of their data would be confused. They'd think they were doing a read, but really someone else was doing a read. They'd get the wrong value. It would be very confused. So by creating a bus arbiter, this allows multiple devices to become the bus master, or to request to become the bus master, and only grants access to one of them at a time. So if I modified the CPU to wait for the bus grant to be given to it before it would put something onto the bus. So here's a circuit that demonstrates the bus arbiter. At first, I just tested it by connecting up 4 CPUs to this same bus arbiter. So they're all requesting to use the bus, and only one of them is granted access to it at a time. So here are the 4 CPUs. This one is performing insertion sort in this memory. This one is performing bubble sort in this memory. And this one is performing radix sort in this memory. This one is performing the copy I/O program, but it's without interrupts, which means that it needs to continually check to see whether there's new input put in. So you can see that these sorts are going a lot slower than the ones before because each one of them is only allowed to use the bus about 1/4 of the time. Another way to, or another thing that the bus arbiter is used for is a disk. Disks can store data, but sometimes they need to read or write values from the memory. In order to speed up this process, rather than the CPU getting it and giving it to the disk, the CPU can tell the disk to become the bus master, and then it can read or write the data directly from the memory. This is called direct memory access. So here's an example of a disk plugin that I created, which the disk has its values stored in a backing store, a file. Anyway, so the data that's stored in the disk. We'll see whether or not that messes this program up. It shouldn't, I hope. This CPU is performing a sort in this memory, as well as telling the disk, oh good, to read in all of the data in this file. Sorry. As well as telling the disk to read in all of the data from its file. So right now the disk just read in all of those characters. These are their numerical representations. And now the CPU is taking the turn to sort this data. When it's finished, it will tell the disk to write all of that, or to read all of the values back from memory and store it into its file, and then we'll be able to open up the file and see that they'll now be in alphabetical order. This will just take a minute. This disk is running in what's called cycle stealing mode, which means that the CPU and the disk are both fighting to become the bus master. So the bus arbiter is really involved, granting access to them one at a time. So when the sort is done, now it's done. Now the disk is reading it back into its file. The CPU is also sorting the data over here at the same time whenever it's allowed to become bus master. If I turn the words on. So the disk looks like it's no longer requesting to be the bus master. So
You want to finish reading the file?
what?
Didn't they finish reading the file?
Yeah, I think so. Now it's just sorting. So this file.
I'm sorry.
Open it up again. Now it's in order. So that's what it's meant to do. Cool. So we determined that DLSim is very successful in demonstrating digital logic on the system architecture level, produced many plugins and many algorithms for the CPU to run. Thank you for watching the presentation, and you can go to dlsim.com if you're interested in trying out DLSim.